All right, so I thought that this was pretty cool during my biochem coursework, so I thought I'd make a little video explaining it. So lysozyme is an example of an acid-base enzyme. It's pretty cool. Lysozyme isn't ending in ASE like most enzymes, but still an enzyme. It is used as a antibacterial agent and a disposal enzyme. And disposal enzyme just means that it cleans up bacterial remains. But I want to talk about how it is antibacterial. So, it catalyzes the hydrolysis of the bacterial cell walls. So it cleaves the cell wall, and then when the wall is cleaved, it leads to a lysis of the cell. So the cell wall, I have a little drawing of it over here, has a NAM portion and a NAG portion, and it's just two cyclic rings, and they're formed by this, I think it's an ether bond. And the lysozyme breaks the NAM's side of this ether bond, and that leaves the NAG portion to have an OH group, and through a long process for NAM, leaves the OH group as well on this carbon. So this is the end result, but this whole process where I just wrote lysozyme can be explained in this diagram here, which we'll go over in a bit. But the active site of the lysozyme enzyme is important to its function, obviously, but it has a large cleft and two acidic amino acids in cleaving the bond. So glutamic acid and aspartic acid are very important. Glutamic acid has an increased pKa in nonpolar environments, and aspartic acid has a normal pKa in nonpolar environments. The reason why the stability of their pKa's in these environments is important is because it's proof that these two amino acids are important in the active site, because changing the pH environment of these two acids decreases the catalytic activity. So aspartic acid is going to stabilize the transition state, so that's what TS means. And glutamic acid is going to act as an acid, and it's going to make that original cut at the top. Okay, so moving over to that transition state of this enzyme, it's going to form a D-ring configuration. So residue 4, so amino acid residue 4, turns into a sterically strained configuration, D-ring. And it's going to stabilize the transition state. So we're going to first go from this initial bond after cleaving to this carbocation. And this carbocation is important to the SN2 reaction that's going to occur later on. Okay, so the entire mechanism is laid out here, and it's important to kind of go through it just because, it's not sufficient to just say, oh, lysozyme, and then the end result. So it's a little bit of organic chemistry, but nothing too difficult. So we have our amino acids, and they're going to bind, and the glutamic acid is going to slice that bond. And then from here, this now turns into our final end product, so we don't need to do anything else to that one, but this one is forming that D-ring, and from that D-ring, we're forming that carbocation. And aspartic acid is going to come in and actually bind to NAM and forming this little unit over here. So at this point, aspartic acid is the nucleophile in the reaction, and it's a pretty good nucleophile too, so that's good. So our final step over here is we're going to have water binding. At this point, aspartic acid is a good leaving group, and we're going to go through another SN2 reaction where water is going to contribute to that hydroxyl group that we need for our end product, and glutamic acid is going to contribute to breaking that water molecule so we can use its components to form that group. And aspartic acid is just going to leave, as I put over there. And then finally, from that state, we have our free amino acids, and we have our two end products. NAM, an egg. And at this point, the bacteria cell wall is not surviving. So thanks for listening.